Before we begin our journey tonight, I'm curious. Where in the world are you listening from right now? And what time is it there? Take a slow breath and let the day gently fade away. Tonight I'll be sharing a calm story about the most ancient galaxies in the universe, distant islands of light, born when the cosmos was still young. We'll drift back through 13 billion years of time, to a universe just waking up where the very first stars ignited in the dark. You'll hear my voice guiding you through these ancient cosmic structures, glowing softly in the primordial darkness, slowly spinning and merging. And then, once the story ends, you'll hear authentic space sounds for the rest of the night. So settle in, close your eyes if you wish, and let's drift back to the beginning of galactic time. In the beginning, there was darkness. Not the darkness of night that we know, but a deeper, more profound darkness that stretched across the entire universe. This was the cosmic dark ages, a time after the Big Bang, but before the first stars had formed. The universe was filled with neutral hydrogen gas, cooling slowly, expanding gently, waiting in silence for something to happen. The temperature had dropped from trillions of degrees to mere thousands, and it continued falling as space itself expanded. For nearly 400 million years, nothing disturbed this primordial quiet. The universe was transparent to microwave radiation, but opaque to visible light, a fog of neutral hydrogen that would scatter any photon trying to pass through it. Tiny fluctuations in density, imprinted during the very first moments after the Big Bang, began to matter more and more. Some regions had slightly more matter than others, perhaps just one part in 100,000 more dense. But gravity, patient and persistent, began its slow work of amplifying these differences. Dark matter, mysterious and invisible, made up most of the mass doing this pulling, 5 times more abundant than ordinary matter. Dark matter feels only gravity, not electromagnetic forces, so it could collapse more easily without being heated or scattered by radiation. The dark matter began to clump together first, creating gravitational wells. Hydrogen atoms began their slow drift inward, drawn by the gravity of these dark matter concentrations. This happened slowly at first over millions of years, atom by atom, molecule by molecule. The clouds contracted gradually, warming ever so slightly from the compression. The gravitational potential energy of the falling gas converted into heat, raising the temperature by degrees, then dozens of degrees, then more. As the gas continued to fall inward, the center of the cloud became denser and hotter. The hydrogen atoms, previously spread across vast distances, were now being pressed closer together. The pressure built gradually, steadily, inevitably. The cloud fragmented into smaller pieces, each one collapsing independently, each one heating up in its core. After perhaps 500 million years of cosmic history, something remarkable happened in the densest cores. The temperature and pressure reached a critical threshold of about 10 million degrees Kelvin. At this temperature, hydrogen nuclei moved so fast, colliding so violently, that they overcame their electrical repulsion and fused together, forming helium and releasing tremendous amounts of energy in the process. The first star ignited. It was a massive star, perhaps 100 times the mass of our sun, maybe even 200 solar masses. Far larger than any star that could form in the modern universe. It was made of nothing but hydrogen and helium, the primordial elements created in the Big Bang. No carbon, no oxygen, no iron. Astronomers call these population 3 stars, the first stellar population. though none have ever been directly observed because they all died billions of years ago. This pristine composition meant the star had no dust to help it radiate away heat during formation, so only very massive stars could form in this first generation. The star burned fiercely, brilliantly, blazing with a blue-white light that pushed outward through the surrounding hydrogen fog. Its surface temperature exceeded 50,000 degrees, far hotter than our sun's modest 6,000 degrees. The intense ultraviolet radiation from this star ionized the hydrogen gas around it, stripping electrons from atoms, creating a bubble of clarity in the cosmic fog. The ionized region expanded outward at nearly the speed of light, growing larger with each passing year. But this star was not alone for long. The same gravitational collapse that created it was happening in nearby regions of the same dark matter halo. Other dense knots of gas were reaching the critical temperature and pressure for fusion. More massive stars ignited, then more, their light adding to the growing bubble of ionization. Within perhaps a few million years, there were hundreds of these brilliant stars, then thousands, then tens of thousands, all burning together in a relatively small volume of space, perhaps just a few thousand light years across. A galaxy was being born, the first galaxy in the universe. This first galaxy was nothing like the grand spiral galaxies we see in the modern universe. It had no elegant spiral arms, no orderly disk, no smooth distribution of stars. It was a chaotic, irregular collection of brilliant, massive stars, surrounded by glowing ionized hydrogen gas. The stars orbited around their common center of mass, held together by mutual gravitational attraction. The much stronger gravity of the dark matter halo kept everything bound together. The galaxy might be only a few thousand light years across, tiny compared to the Milky Way's 100,000 light years span, containing perhaps 1 million stars rather than hundreds of billions, but it blazed with extraordinary luminosity because all its stars were young, hot, and massive. The light from these stars traveled outward in all directions, pushing through the neutral hydrogen that still filled most of the universe. Wherever this starlight encountered hydrogen atoms, it ionized them. The bubble of ionized space around the young galaxy continued to expand. This was the beginning of the epoch of reionization, the period when the first galaxies began to clear away the fog that had filled the universe. Imagine floating in space at this early epoch, 600 million years after the Big Bang, watching this ancient galaxy from a distance of a few million light years. It appears as a small, irregular patch of blue-white light, fuzzy at the edges. The glow of ionized hydrogen creates a halo around the central concentration of stars. The galaxy doesn't have sharp boundaries, instead fading gradually into the surrounding space. It pulses gently with the birth and death of stars, the massive population 3 stars living fast and dying young, burning through their nuclear fuel in just a few million years, rather than the billions of years that smaller stars enjoy. Supernovae are common events in this galaxy. Every few thousand years, one of the massive stars exhausts its hydrogen fuel. It begins fusing helium, then carbon, then heavier elements in its core, building up layers like an onion. Finally, the core collapses and the star explodes in a brilliant supernova, briefly outshining the entire rest of the galaxy. These supernovae are absolutely crucial to the evolution of the galaxy and the universe. They create the first heavy elements, the first atoms beyond hydrogen and helium. In the cores of these dying stars, through nuclear fusion, driven by intense temperatures and pressures of collapse, carbon atoms form, then oxygen, nitrogen, neon, magnesium, silicon, sulfur, and finally iron. Elements heavier than iron are created in the supernova explosion itself, as free neutrons produced in the blast are captured by existing nuclei. Gold, platinum, uranium, all the heavy elements that will someday make up planets and living things, are forged in these stellar deaths. The supernova explosion scatters these newly created elements into the surrounding space at thousands of kilometers per second. The expanding shell of gas plows into the interstellar medium, shocking and compressing it, sometimes triggering new waves of star formation. The next generation of stars that forms in this galaxy will incorporate these elements, becoming population 2 stars, slightly more complex, slightly more similar to the stars we know today. These second-generation stars are smaller on average because the presence of heavy elements allows the gas to radiate heat more efficiently during collapse, permitting smaller stars to form. As you watch this galaxy over millions of years, you notice it's not remaining still in space. It's moving, following gravitational currents created by the distribution of dark matter. The dark matter that makes up most of the galaxy's mass extends far beyond the visible stars, forming a roughly spherical halo, perhaps 10 times larger than the region where stars are actively forming. This dark matter halo is itself part of larger structures, filaments and sheets of dark matter connecting different regions of the universe. The galaxy's motion follows these invisible pathways. The galaxy is not alone in the universe. As your view expands, you begin to see other small points of light scattered through the darkness. Other young galaxies forming in other dark matter halos. They're not evenly distributed, but instead cluster along the dark matter filaments like beads on cosmic strings. The universe is lighting up, slowly but steadily, as more and more regions of gas collapse and ignite their first stars. Each new galaxy adds its light to the growing illumination, pushing back the darkness a little further, contributing its share of ionizing radiation to the reionization process. The nearest galaxy to the one you're observing is about 10 million light-years away, a similar small irregular collection of hot young stars. Between the two galaxies, space is still filled with neutral hydrogen, but both galaxies are contributing to ionizing it. Their bubbles of ionization are expanding toward each other, and eventually, perhaps in another 100 million years, those bubbles will merge, creating a larger region of ionized space. Time passes, measured in millions and tens of millions of years. Your galaxy continues to shine, continues to form new stars from its reserves of hydrogen gas. The gas is continually replenished as more falls into the dark matter halo from the surrounding space. The galaxy slowly grows more massive, accumulating both stars and gas. But now something new begins to happen. That nearby galaxy, the one 10 million light-years away, has been moving through space, and its path is bringing it closer. The two galaxies, drawn together by their mutual gravitational attraction, are on a collision course. In the vast emptiness of space, galaxy collisions might seem unlikely. But in this early, denser universe, they're actually quite common. The universe is smaller now than it will be in the future. Space itself is more compact, and galaxies are closer together. These two small proto-galaxies are approaching each other, taking millions of years to close the distance between them. As they draw near, their gravitational fields begin to interact more strongly. Their dark matter halos overlap, pulling at each other's stars and gas clouds. You watch as the two galaxies begin their cosmic dance. They don't collide like solid objects because galaxies are mostly empty space. The stars within each galaxy are separated by such vast distances, typically several light years apart. The probability of two stars actually hitting each other during a galaxy collision is negligibly small. Instead, the galaxies pass through each other, their stars and gas clouds intermingling, their orbits curved and altered by gravitational forces at play. The stars themselves sail past each other harmlessly. The gas clouds, however, do collide. Unlike stars, gas clouds are large and diffuse, and when gas clouds from the two galaxies meet, they don't pass through each other. Instead, they collide, compress, shock heat, and mix. These collisions are catastrophically energetic, compressing the gas to much higher densities and temperatures. The shocks trigger bursts of intense star formation. Regions that were not quite dense enough to collapse and form stars before now cross that critical threshold. New stars ignite throughout both galaxies, particularly in the regions where the gas clouds have collided most directly. The combined system blazes with light, the star formation rate temporarily increasing by factors of 10 or even 100. Young massive stars flood the galaxies with ultraviolet light. The system becomes what astronomers would later call a starburst galaxy, forming stars at an unsustainably high rate. New supernovae explode every few years rather than every few thousand years, further enriching the gas with heavy elements, further shocking and stirring the interstellar medium. The two galaxies swing past each other in their first close encounter, then separate again, but they're still bound by gravity. They loop back through space, their paths curved by their gravitational interaction. Coming around for another pass, with each passage they come a little closer, losing energy through a process called dynamical friction. The gravitational interactions between individual stars and dark matter particles gradually slow the galaxy's relative motion. Over hundreds of millions of years they spiral together, orbiting each other in increasingly tight loops, until finally they merge completely into a single, larger galaxy. The final merged product is still irregular and chaotic, its stars orbiting in random directions rather than in an organized disk, but it's more massive than either of the original galaxies. It now contains perhaps 2 million stars rather than 1 million, has accumulated more gas from both progenitors. It sits in a dark matter halo, that's the combined mass of both original halos. This merged galaxy will continue its evolution, perhaps merging with other small galaxies in the future, slowly building up mass and complexity. This is how galaxies grow in the early universe, through a process called hierarchical merging. Small protogalaxies combine to form larger structures, which in turn merge to form even larger galaxies. It's a slow process, operating on timescales of hundreds of millions to billions of years, but it's relentless and universal. Over cosmic time, through countless mergers, these tiny first galaxies will build up the massive galaxies we see in the universe today. Giant spirals like the Milky Way and enormous ellipticals containing trillions of stars all trace their lineage back to these small, irregular systems. Now let's drift to another part of the early universe, to a region that will eventually be observed by human astronomers billions of years in the future. Using the James Webb Space Telescope, This region will reveal its secrets. Here, in a particularly dense region of the cosmic web, something unusual is happening. Multiple proto-galaxies are forming very close together, so close that their gravitational fields overlap significantly. Instead of evolving independently and perhaps merging later, these galaxies are forming almost simultaneously. As parts of a larger whole, gas flows into this region from multiple directions, funneled along dark matter filaments that converge here like rivers flowing toward a central basin. The gas doesn't fall uniformly, but instead creates streams and filaments of its own, glowing faintly as it moves through space, heated by shocks and compression. Where these gas filaments intersect and collide, conditions are ideal for star formation. Dense knots of gas collapse rapidly, igniting bursts of stellar birth. The result is a complex system of multiple star-forming regions. What will later be recognized as a single galaxy is forming from the inside out, with several distinct cores that will eventually merge. This galaxy is already showing signs that it will become one of the massive early galaxies that will puzzle astronomers in the distant future. It sits at the center of a particularly dense node in the cosmic web. More and more gas is flowing toward it constantly along the dark matter filaments. The rate of star formation here is extraordinary, hundreds of solar masses of new stars forming every year, far exceeding the typical rates in galaxies of later epochs. If you could see this galaxy in visible light, it would be one of the brightest objects in this region of the early universe, a beacon of stellar birth shining across the cosmos. But there's something else happening at the very center of this forming galaxy, something that will profoundly influence its future evolution. Deep in the core, where the density of gas and stars is highest, where multiple streams of inflowing material are converging, something incredibly massive and compact is taking shape. The exact mechanism is still debated by astronomers, but somehow in this dense, chaotic environment, a supermassive black hole is forming. This is not a stellar mass black hole formed from the collapse of a single massive star, but something far larger, perhaps already 100,000 or even 1,000,000 times more massive than the Sun. And it's growing rapidly, consuming matter at a prodigious rate. Perhaps it formed from the direct collapse of a particularly massive cloud, a primordial gas, one that was too hot to fragment into stars. Or perhaps it grew from the merger of many smaller black holes, formed from population 3 stars that lived and died in the galaxy's earliest days. Perhaps it formed from a supermassive star, hundreds of thousands of solar masses, that collapsed directly to a black hole. Whatever its origin, this black hole is already enormous. Matter spirals into the black hole, forming an accretion disk of gas around it that glows with incredible intensity. As this gas falls inward, drawn by the black hole's immense gravity, it accelerates to significant fractions of the speed of light. Friction within the disk heats the gas to temperatures of millions of degrees. The accretion disk glows brilliantly across the electromagnetic spectrum, from radio waves to X-rays, releasing energy with extraordinary efficiency. For every kilogram of matter that falls into the black hole, about 10% of its rest mass energy is converted to radiation. This is far more efficient than nuclear fusion, which converts less than 1% of mass to energy. Jets of material shoot outward from the poles of the black hole's accretion disk. Perpendicular to the plane of the disk, these jets are driven by complex interactions between the black hole's spin, the magnetic fields in the accretion disk, and the tremendous energy densities near the event horizon. The jets move at nearly the speed of light, carrying energy and material far out into the surrounding galaxy and beyond. This is one of the first quasars in the universe. One of the most luminous objects that can exist, the quasar at the center of this galaxy, is so bright that it outshines all the stars in the galaxy combined. If you could observe it from billions of light years away, even from across the observable universe, you could still detect it. A brilliant point of light marking the location of a supermassive black hole, actively consuming matter. Its light and energy profoundly influence the entire galaxy around it. The radiation pressure from the quasar, the energy carried by its jets and winds, pushes gas out of the central regions, suppressing star formation there even as the jets and shocks trigger it elsewhere. This phenomenon, where the black hole regulates star formation in its host galaxy, is called a GN feedback. Active galactic nucleus feedback plays a crucial role in galaxy evolution. As the black hole grows more massive and luminous, it drives more powerful winds and jets, blowing more gas out of the galaxy or heating it to temperatures too high for star formation. Eventually, the feedback can become so strong that it effectively shuts down both the black hole's growth and the galaxy's star formation, leaving behind a massive but relatively quiescent galaxy dominated by older stars. But we're witnessing this galaxy in its youth, when both star formation and black hole growth are proceeding vigorously. Over the next few 100 million years, this galaxy will continue to grow through a combination of internal processes and mergers with smaller neighbors. It will become one of the massive galaxies that populate the early universe. The kind of galaxy that seems too large and too mature to exist so early, challenging our theories of galaxy formation. Future astronomers will catalog this galaxy with designations like Jade's G11 or similar names, marveling at how such a massive structure could have assembled in just a few 100 million years after the Big Bang. The galaxy will become a touchstone for understanding early cosmic evolution. Let's shift our perspective now, pulling back to view not just individual galaxies, but the larger cosmic structure across a significant volume of space. If we could see the entire universe as it was during this early epoch, perhaps 700 million years after the Big Bang, we would see a remarkable pattern emerging. Galaxies are not distributed randomly through space, but instead trace out a vast web-like structure, the cosmic web, one of the most beautiful and fundamental patterns in nature. This cosmic web directly reflects the distribution of dark matter. Dark matter, responding only to gravity, has clumped together under its own gravitational attraction, forming filaments and sheets and nodes with vast empty voids between them. Where the dark matter is densest along the filaments, and especially at the nodes where filaments intersect, the gravity is strongest. Ordinary matter, the hydrogen and helium gas, falls into these regions most readily. Galaxies form preferentially in these locations, so the distribution of galaxies mirrors the distribution of dark matter, revealing the otherwise invisible scaffolding on which the visible universe is built. The cosmic web looks something like a three-dimensional spider web or a neural network, with galaxies as bright points along the strands and filaments. The filaments themselves, the regions between galaxies but still part of the overdense structures, glow faintly with diffuse gas. This material has been pulled along by dark matter's gravity but hasn't yet collapsed into galaxies. The gas is warmer than the gas in voids, heated by shocks and compression as it flows along the filaments. It emits faint radiation that will someday be detectable by sufficiently sensitive instruments. Drifting through this cosmic web, you pass through regions of very different character. In the dense filaments, galaxies are relatively close together by cosmic standards, perhaps only a few million light years apart. Close enough that their gravitational fields can interact. Minor mergers are common here, with small galaxies being tidally disrupted and absorbed by larger ones. The galaxies in these regions tend to be more massive on average, having grown through multiple collisions and having access to more gas flowing along the filaments. The space between galaxies in a filament glows faintly with warm ionized gas, forming what's called the warm-hot intergalactic medium. This gas is at temperatures of hundreds of thousands of degrees, too hot to form stars, but not hot enough to emit X-rays efficiently. It contains a significant fraction of the universe's ordinary matter, the so-called missing baryons that astronomers would later spend decades trying to locate. The gas is enriched with heavy elements from supernova and nearby galaxies, metals blown out into intergalactic space by galactic winds. Then you drift beyond the filament into a void, one of the vast underdense regions between the strands of the cosmic web. The transition is gradual but noticeable. Galaxies become rarer, the distances between them increasing from millions to tens of millions of light years. The diffuse glow of intergalactic gas fades away. The void is darker, emptier, colder, closer to the average density of the universe or even somewhat below it. In the void, the few galaxies that exist are smaller and less luminous on average. They've formed in rare local density peaks within the generally underdense void environment. These galaxies have access to less gas, experience fewer mergers, and evolve more slowly and quietly than their counterparts in filaments and clusters. Some void galaxies will remain small and isolated throughout cosmic history, slowly consuming their gas reserves but never experiencing the dramatic growth through mergers. That's common in denser environments. You drift through the void for what seems like an eternity, traveling across perhaps 100 million light years of nearly empty space. The few photons of light that reach you here have traveled from very distant galaxies, their light redshifted by the expansion of space as they journeyed toward you. The expansion of the universe is most apparent here in the voids, where there's little matter to gravitationally resist the expansion. The voids are growing larger over time, expanding faster than the universe's average expansion rate, while the filaments and nodes resist expansion or even slowly contract under their own gravity. The temperature in the void is just a few degrees above absolute zero, the coldest regions in the entire universe. The cosmic microwave background radiation, the afterglow of the Big Bang, bathes everything in photons. At this epoch, the temperature is about 20 Kelvin, much warmer than the 3 Kelvin it will have in the modern universe due to ongoing expansion and cooling. But apart from this background radiation, the void is nearly empty, nearly dark, a place of profound silence and stillness. Eventually, you reach the far side of the void and enter another filament of the cosmic web. Suddenly there's structure again, light again, galaxies appearing in your field of view like cities seen from orbit. Here you encounter a cluster of young galaxies, dozens of them orbiting around a common center of mass. This is one of the first galaxy clusters in the universe, a protocluster that will eventually grow into one of the massive galaxy clusters containing thousands of members that populate the modern universe. The galaxies in this protocluster are interacting strongly with each other. Their gravitational fields pull at one another, stretching and distorting the smaller galaxies, sometimes stripping away stars and gas to create long tidal tails of material stretched between galaxies. These tidal interactions can be beautiful and destructive, capable of triggering star formation through compression while simultaneously removing the gas needed for future star formation. The space between the galaxies in this cluster is not empty. It's filled with hot gas, heated to temperatures of millions of degrees by the tremendous gravitational potential energy of the cluster. As gas falls into the cluster, accelerating toward the center under the combined gravity of all the cluster's mass, it shocks and heats up, converting gravitational potential energy into thermal energy. This intracluster medium glows brightly in X-rays, though you cannot see X-rays with human eyes. If you could, the cluster would appear not as isolated points of light, but as a single diffuse glowing region, with the galaxies as bright knots within it. At the center of the cluster, the largest galaxies are already showing signs of interaction. The most massive galaxy sits at the center of the gravitational potential, slowly pulling in smaller neighbors. Over the next billion years, this central galaxy will grow enormously through a series of mergers, eventually becoming what's called a brightest cluster galaxy, or BCG, a supergiant elliptical that can contain trillions of stars and extend for millions of light years. These BCGs will become the most massive single galaxies in the universe, sitting at the centers of the richest galaxy clusters, dominating their environments. Let's focus now on one particular galaxy in this cluster, a galaxy that will have an interesting fate. It's a small spiral galaxy, one of the first in the universe to develop that characteristic rotating disk shape. Most galaxies in this early epoch are irregular, chaotic collections of stars without much organized structure. But this one has managed to settle into a more orderly configuration over several 100 million years of relatively quiet evolution. The galaxy is beautiful in its simplicity and youth. Its disk extends for perhaps 20,000 light years, small compared to mature spirals, but well organized for this early epoch. Gas and stars orbit around its center in roughly circular paths, all moving in the same direction, the result of conservation of angular momentum as the galaxy formed from a rotating cloud of gas. The rotation is smooth and regular, the disk completing one full rotation every few 100 million years. The slight gravitational perturbations from density variations within the disk have begun to create spiral structure. These aren't the well-defined, grand design spirals we see in famous galaxies, but rather weak, fragmentary spiral arms, regions where the density of stars and gas is slightly enhanced. But they're recognizable as the beginning of spiral structure, the first hints of the beautiful patterns that will characterize disk galaxies throughout cosmic history. The spiral arms glow with clusters of young blue stars and pink emission nebulae where new stars are forming. The stars in these arms are more massive and luminous on average than stars forming in the modern universe, still somewhat influenced by the lower metallicity of the gas, though this galaxy has been enriched by several generations of supernova. Between the arms, the disk appears darker in visible light, populated by older yellow and red stars and lanes of dust created from the heavy elements expelled by previous stellar generations. The central bulge of the galaxy is yellowish, filled with somewhat older stars that formed early in the galaxy's history, when star formation rates were highest. Before the disk had fully settled into its current configuration. In the very center sits a black hole, not as massive as the quasars we've observed, but substantial nonetheless. Perhaps 1,000,000 times the mass of the Sun. This central black hole is relatively quiet at the moment, accreting gas slowly, not producing powerful jets or radiation. If you could dive down into one of the spiral arms of this galaxy, you would find yourself among active star-forming regions. Here, enormous molecular clouds, complexes of cold hydrogen molecules each tens of light years across, are collapsing under their own gravity. Fragmenting into thousands of smaller clumps, within these clumps protostars are forming. Young stars still gathering mass from their surrounding envelopes of gas and dust. The most massive stars in each cluster ignite first, their intense ultraviolet radiation beginning to ionize and clear away the surrounding gas, creating beautiful emission nebulae, glowing clouds of ionized hydrogen that mark sites of recent star formation. These massive stars will live for only a few million years before exploding as supernova. But during their short lives, they dominate the light and energy output of the star-forming region. Around the lower mass stars, stars more similar to our Sun, disks of material are forming. Protoplanetary disks where planets will eventually coalesce. The first exoplanets in this galaxy are beginning to form, rocky worlds and gas giants taking shape from the dust and gas orbiting young stars. Some of these planets will be Earth-like, with solid surfaces and atmospheres, though the low metallicity of the galaxy means rocky planets are somewhat rarer than they'll be in later epochs, when the interstellar medium has been more thoroughly enriched with heavy elements. This spiral galaxy, peaceful and orderly, represents what many early galaxies might have become if left to evolve undisturbed. Slowly forming stars, slowly enriching their gas with heavy elements, slowly building up stellar populations, and perhaps nurturing the development of life. But this galaxy's peaceful existence is about to be disrupted, because it's a member of the protocluster we've been observing, and that environment will transform it dramatically over the coming billion years. The galaxy is currently on an orbit that takes it through the outer regions of the cluster, but its path is gradually bringing it closer to the cluster center. The cluster's enormous gravitational pull is slowly drawing it inward. Each time the galaxy passes through a denser region of the cluster, gravitational interactions with other galaxies and with the cluster's dark matter slightly alter its orbit, on average moving it toward the center. This process is slow but inexorable. Eventually, perhaps a few 100 million years from now, the galaxy will plunge through the densest part of the cluster at high speed. When it does, its motion through the hot intercluster medium will create a pressure like a wind blowing against it. The gas in the galaxy's disk will feel this ram pressure, this drag force created by plowing through the intercluster medium at hundreds or thousands of kilometers per second. For the stars in the galaxy, this passage through the cluster center is unremarkable. Stars are so small and so far apart that they don't collide with gas particles in the intercluster medium. They sail through largely unaffected, continuing their orbits around the galaxy's center. But the gas in the galaxy's disk is a different story. The diffuse gas that hasn't yet formed into stars, the reservoir for future star formation, is more loosely bound to the galaxy than the stars are. The ram pressure from the galaxy's motion through the intercluster medium is strong enough to overcome the galaxy's gravity in its outer regions. As the galaxy plunges through the cluster center, streams of gas are stripped away from it, pulled out of the disk and left behind in a long tail, like a comet's tail, but made of hydrogen rather than ice. The gas glows as it's stripped away, heated by the ram pressure and by friction with the intercluster medium. The galaxy is literally having its future stolen from it, losing the raw material it would need to continue forming stars. This process is called ram pressure stripping. One of the primary ways that cluster galaxies are transformed from active star-forming spirals into passive, quiescent systems. The galaxy continues on its orbit, looping back out toward the cluster outskirts, then falling in again with each passage through the dense central regions. More gas is stripped away. The outer parts of the disk, where the gas is most loosely bound, lose their gas first. The stripping proceeds from the outside in, gradually removing the interstellar medium from larger and larger fractions of the disk. Over hundreds of millions of years, through multiple passages, the galaxy loses most of its gas. The star formation rate, no longer sustained by fresh supplies of hydrogen, begins to decline. The spiral arms, which were maintained by ongoing star formation, highlighting the density waves in the disk, begin to fade. Without new young blue stars being born to replace the ones that die, the blue colors of the spiral arms gradually disappear. The galaxy's appearance transforms dramatically over time. The brilliant blue light from young massive stars, stars that live for only a few million years, fades first as these stars reach the end of their lives and explode as supernova. The galaxy becomes dominated by older, longer-lived stars that are yellower and redder in color. Its integrated color shifts from blue to yellow to red as the stellar population ages. No new stars are born to replace the ones that die. After perhaps 1 billion years, this galaxy will be completely transformed into what astronomers call a red and dead galaxy. Filled with old stars but forming no new ones, its spiral structure dissolved, its disk gradually puffed up into a more spheroidal shape through gravitational interactions with other cluster members. This galaxy will continue to exist for billions of years more, orbiting within the cluster, occasionally colliding with other galaxies and merging with them. But it will never again experience the vigorous star formation of its youth. Its story is the story of environmental transformation, how a galaxy's surroundings can completely alter its evolutionary path. In the field, far from clusters, a similar galaxy might have continued forming stars for 10 billion years or more. But in the dense cluster environment, its star formation was quenched within 1 billion years, its future altered by forces beyond its control. This fate awaits many galaxies that fall into clusters in the early universe and throughout cosmic time. The cluster environment is hostile to star formation, stripping away gas through ram pressure, heating gas through tidal interactions and gravitational shocks, removing gas through galaxy-galaxy collisions. As a result, the centers of galaxy clusters, both in the ancient universe and in the modern era, are dominated by red, elliptical, and lenticular galaxies, while blue star-forming spirals are more common in lower-density environments. But not all ancient galaxies meet such an end. Let's drift away from this cluster now, traveling across hundreds of millions of light-years of space, out to a more isolated region of the cosmos. We're moving forward in time slightly as well, to perhaps 900 million years after the Big Bang, when the universe has had more time to evolve and galaxies have grown larger and more complex. This galaxy formed in a region where dark matter was moderately dense, enough to support robust galaxy formation, but not so dense as to create a cluster environment. It's been evolving in relative isolation for hundreds of millions of years, experiencing occasional minor mergers with smaller satellites, but no major collisions that would disrupt its structure. The result is a galaxy that's had time to settle into a stable, coherent configuration. The galaxy has developed into a beautiful spiral, larger than the cluster spiral we just observed. Its disk now extends for 50,000 light-years, and it has developed two prominent spiral arms wrapping around a bright central bulge. The spiral pattern is stronger and more defined than in younger spirals, the result of density waves propagating through the disk, regions of enhanced gravity that compress gas and trigger star formation as the disk material passes through them. The rotation of this galaxy's disk is smooth and steady, a consequence of the conservation of angular momentum from the primordial gas cloud that collapsed to form it. The inner regions rotate faster than the outer regions in terms of actual speed, but all regions take roughly the same time to complete an orbit due to the distribution of mass. The pattern speed of the spiral arms is different from the rotation speed at any given radius, which is why the spiral arms persist rather than winding up and disappearing over time. Material orbits through the arms, spending time there before moving on, but the arms themselves maintain their shape and position as density waves in the disk. What makes this galaxy particularly interesting is its stability and longevity. Unlike galaxies in dense cluster environments, it hasn't experienced major environmental disruptions. It hasn't had its gas stripped away by ram pressure, hasn't been torn apart by tidal forces from nearby massive neighbors. Instead, it's been able to maintain a steady rate of star formation, converting gas into stars at a sustainable pace that could continue for billions of years. The galaxy is steadily growing more massive over time. Gas continues to accrete onto it from the surrounding intergalactic medium, falling along dark matter filaments that connect this galaxy to the larger cosmic web. Some of this gas is primordial, hydrogen and helium that have never been part of a galaxy before. Some of it is recycled material, gas that was expelled from other galaxies by supernova or galactic winds, and has now found its way here. As you approach this galaxy more closely, you can see the details of its structure with greater clarity. The spiral arms are marked by bright blue clusters of young stars, O and B type stars that are tens of thousands of times more luminous than our Sun. These stellar associations are strung along the spiral arms like pearls on a string, marking the locations where giant molecular clouds have recently collapsed to form stars. Interspersed with the blue star clusters are glowing pink and red emission nebulae, vast clouds of hydrogen gas ionized by the ultraviolet radiation from nearby hot stars. These high regions, as astronomers call them, can span hundreds of light years and contain enough gas to form thousands of stars. They're the most visible signposts of ongoing star formation, glowing beacons that make spiral arms stand out against the background of older stars. Between the spiral arms, the disk appears darker in visible light, though it's far from empty. This interarm region is populated by older stars, stars that formed millions or billions of years ago when they were in a spiral arm and have since orbited out of the arm into the space between. There are also stars of all ages here, because star formation isn't completely confined to the spiral arms, just enhanced there. Lanes of dust, created from the heavy elements produced by previous generations of stars, run through both the arms and the interarm regions, appearing as dark ribbons silhouetted against the glow of background stars. The central bulge of the galaxy is more complex than it first appears. It's not a simple smooth sphere of stars, but has structure of its own. In the very center is a small bar, an elongated concentration of stars only a few thousand light years long. This bar rotates as a solid body, all the stars in it orbiting at the same angular speed, maintaining their relative positions. The bar plays an important role in the galaxy's dynamics. Its gravity creates resonances in the disk, helping to drive the spiral pattern and funneling gas toward the center, feeding both star formation in the central regions and the supermassive black hole at the galaxy's very core. Speaking of that central black hole, it's currently in a relatively quiet state. It has a mass of perhaps 10 million times that of the Sun, substantial, but not actively accreting large amounts of material at the moment. Occasionally, a star or gas cloud wanders too close to it and is torn apart by tidal forces, the material spiraling into the black hole and causing a brief flare of radiation. But most of the time, the black hole is quiescent, a sleeping giant at the heart of the galaxy. Its presence detectable mainly through its gravitational influence on nearby stars, which orbit the galactic center at high speeds. This spiral galaxy, stable and isolated, represents an ideal evolutionary track for disk galaxies. Over the next several billion years, it will continue forming stars at a steady rate, gradually converting its gas into stellar populations. It will experience occasional minor mergers with satellite galaxies, small, irregular galaxies orbiting in its dark matter halo. Each merger will trigger brief bursts of enhanced star formation and add new stars to the galaxy's inventory. The galaxy will slowly grow larger and more massive, accumulating both the stars from mergers and new stars formed from accreted gas. Its spiral structure will persist, maintained by the ongoing star formation and the density waves in the disk. Its central black hole will occasionally flare into activity when gas is funneled to the center, but it will spend most of its time in a quiescent state. In many ways, this galaxy's future evolution will be similar to that of our own Milky Way. It's on track to become a large spiral galaxy, 100,000 light-years across or more, containing hundreds of billions of stars, home to countless planetary systems, some of which might develop life and intelligence. It represents the success story of galaxy evolution, a galaxy that formed early, settled into a stable configuration, and has been able to grow and evolve without major disruptions. Now let's shift our view to explore a very different type of ancient galaxy, one that represents the extreme end of the galaxy population in the early universe. We need to search for this galaxy carefully because it's rare and difficult to detect. It exists at nearly 1 billion years after the Big Bang, in one of the densest regions of the cosmic web, where multiple dark matter filaments converge, creating an environment unlike anywhere else. This galaxy is what astronomers call an extreme starburst, a galaxy forming stars at a rate so high that it seems almost impossible. Where a typical galaxy at this epoch might form a few tens of solar masses worth of stars per year, this galaxy is forming thousands of solar masses per year. perhaps even approaching 10,000 solar masses per year. At this rate, the galaxy would convert all its available gas into stars in just tens of millions of years, a cosmic eye blink. The reason for this extreme star formation is the extraordinary supply of gas available to this galaxy. It sits at a major node in the cosmic web where multiple filaments intersect. Gas is flowing into the galaxy from all directions along these filaments, delivering fresh fuel for star formation at an enormous rate. The inflowing gas is also dense and already somewhat compressed from shocks as it flows along the filaments, making it particularly efficient at forming stars once it reaches the galaxy. From a distance, this starburst galaxy appears as an extremely bright, compact source of light. Its extreme luminosity comes not just from stars and visible light, but across the entire electromagnetic spectrum. The galaxy is so dusty, filled with dust from the heavy elements produced by countless supernovae. Much of the ultraviolet and visible light from its stars is absorbed by dust grains and re-emitted in the infrared. In fact, this galaxy emits more energy in the infrared than in all other wavelengths combined, making it what's called an ultraluminous infrared galaxy, or ULIRG. The dust is heated to temperatures of several tens of degrees Kelvin by the absorbed starlight. It radiates this energy as thermal infrared emission. If you could see in the far infrared and sub-millimeter wavelengths, this galaxy would be one of the brightest objects in the sky, outshining almost everything else. These sub-millimeter galaxies, as they're sometimes called, represent a significant population in the early universe, contributing substantially to the overall cosmic star formation rate despite being relatively rare. If you could somehow see through or past the dust to observe the galaxy's interior, you would find an environment unlike anything in normal galaxies. The density of stars in the central few thousand light years is extraordinary, with stars packed hundreds or thousands of times more densely than in the solar neighborhood of the Milky Way. Massive stars are everywhere, flooding the region with ultraviolet light. Supernovae explode constantly, every few years somewhere in the galaxy, each one adding to the turbulence and energy of the interstellar medium. The interstellar gas is hot, dense, and in constant motion, stirred by supernova shocks, stellar winds, and the overall turbulent nature of such extreme star formation. Gas clouds collide and merge, fragment and collapse, in a chaotic dance of creation and destruction. The magnetic fields in the gas are strong, amplified by dynamo processes in the rapidly rotating turbulent medium. They help structure the gas and influence how it collapses to form stars. At the very center of this starburst galaxy, hidden behind layers of dust so thick that not even X-rays can easily penetrate, the supermassive black hole is also growing rapidly, accreting matter at close to the theoretical maximum rate, the Eddington limit, where the radiation pressure from the accretion disk becomes so strong that it threatens to blow away any additional infalling material. The black hole has grown to perhaps 100 million solar masses. It's surrounded by a thick torus of dusty gas that absorbs much of the radiation from the accretion disk. This is a galaxy in transition, experiencing what astronomers call a major merger, the collision and merging of two substantial galaxies of similar mass. The starburst has been triggered by this merger, which funneled enormous amounts of gas to the central regions, where it's now forming stars at an unsustainable rate. The two original galaxies are in the process of coalescing, their stellar populations mixing, their gas clouds colliding and merging, their central black holes spiraling toward each other through the combined nucleus. This starburst phase won't last long. Within perhaps 100 million years, the galaxy will have consumed most of its available gas. The star formation rate will decline precipitously, dropping from thousands of solar masses per year to perhaps tens or even single digits. The galaxy will fade from the list of the most luminous infrared galaxies, its brief moment of extreme brilliance coming to an end. But the merger will leave a lasting imprint. When the two central black holes finally merge, an event that will release more energy and gravitational waves than the combined light output of all the stars in the observable universe for that brief moment. The resulting black hole will be enormous, perhaps hundreds of millions of solar masses. This supermassive black hole will then go through a quasar phase, blasting the remaining gas out of the galaxy with powerful jets and winds, effectively ending star formation and leaving behind a massive but quiescent elliptical galaxy. This galaxy we're observing now will become one of the most massive galaxies in the universe, what's called a compact elliptical in its immediate post-starburst state. Eventually a giant elliptical as it continues to merge with other galaxies and grow even larger over billions of years. It represents one pathway of galaxy evolution, the pathway of rapid growth through mergers and starbursts, contrasting with the more sedate, steady growth of isolated spirals we observed earlier. Let's explore one more remarkable type of ancient galaxy before we conclude our journey through the early cosmos. To find this one, we need to look even further back in time, to perhaps only 400 or 500 million years after the Big Bang, when the universe was barely 3% of its current age. At this early epoch, most galaxies are small, irregular systems, proto-galaxies just beginning their assembly. But astronomers searching with the most powerful telescopes have discovered something unexpected. Galaxies that seem too massive, too organized, too evolved to exist so early in cosmic history. This galaxy, which future astronomers using the James Webb Space Telescope will designate with catalog numbers like JADESGC13 or GNZ11, is one of these surprisingly mature early galaxies. It has a mass of perhaps 1 billion solar masses, remarkable for forming so early. Its light, by the time it reaches observers billions of years in the future, will be redshifted by more than a factor of 13, meaning the universe has expanded by that factor during the light's journey across cosmic time. What makes this galaxy so puzzling to future astronomers is not just its mass, but its properties and characteristics. It shows signs of having already gone through multiple episodes of star formation, with both very young stars producing intense ultraviolet light and somewhat older stellar populations that have already evolved off the main sequence. It has already built up a measurable amount of heavy elements in its interstellar medium, meaning multiple generations of massive stars have lived and died, enriching the gas with carbon and oxygen and iron. It may even show signs of a rotating disk, some degree of organized structure that shouldn't have had time to develop yet according to standard theories of galaxy formation. This galaxy challenges our understanding of how quickly galaxies can form and evolve in the early universe. To accumulate 1 billion solar masses in stars by just 500 million years after the Big Bang requires either extraordinarily efficient star formation with conversion rates far higher than observed in the modern universe, or an earlier start than we thought possible, with star formation beginning perhaps just 200 million years after the Big Bang. If star formation began that early and proceeded at 1,000 solar masses per year, that would barely be enough time to build up the observed stellar mass. But we're not sure if star formation could have started that early. The first stars required dark matter halos to form, and those halos take time to grow through gravitational collapse. Or if star formation could have proceeded that efficiently without being disrupted by supernova feedback, the puzzle deepens when we consider the central black hole that appears to power this galaxy's active nucleus. This galaxy shows signs of a GN activity in its spectrum, meaning it has a supermassive black hole that's already massive and actively accreting matter. But how could such a massive black hole have formed so quickly in the early universe? Black holes grow by accreting matter, but there's a fundamental limit to how fast they can grow set by physics. The Eddington limit, where radiation pressure from the accretion disk becomes strong enough to blow away in falling material. Even if a black hole started growing from the very earliest possible time, starting from say 100,000 solar mass seed, formed from the collapse of a very massive population 3 star, or from direct collapse of a primordial gas cloud, and grew continuously at the maximum Eddington rate without ever stopping. It's difficult to reach the observed masses of millions or tens of millions of solar masses so early in cosmic history. This suggests either that black holes can somehow grow faster than the Eddington limit under certain conditions, perhaps through super-Eddington accretion in dense gas-rich environments, or that the initial seeds were much more massive than we typically assume, perhaps forming from direct collapse of gas clouds with masses of tens of thousands or even hundreds of thousands of solar masses. These observational puzzles may indicate that our theories of early galaxy formation and black hole growth need significant revision, or they may simply reflect the natural scatter in galaxy properties. The fact that some galaxies in the densest environments, at the nodes of the cosmic web, where matter is flowing in from all directions, can grow much faster than the average galaxy in a more typical environment. Future observations with even more powerful instruments will help astronomers understand whether these massive early galaxies are truly as common and as massive as they appear, or whether there are observational biases, selection effects, or systematic uncertainties affecting our measurements and interpretations. As we observe this ancient, surprisingly evolved galaxy glowing in the primordial universe, we are reminded that the cosmos is full of surprises and that our theories, while generally successful, are always provisional, subject to revision in light of new data and observations. The galaxies of the early universe continue to teach us about the processes of cosmic evolution, about how structure forms from simplicity, how complexity emerges from the interplay of gravity, gas dynamics, star formation, and feedback mechanisms. Let's take a moment now to consider the process of cosmic chemical enrichment that these ancient galaxies are driving. In the beginning, after the Big Bang, the universe contained only the lightest elements, about 75% hydrogen and 25% helium by mass, with trace amounts of lithium and beryllium. Everything else, all the heavier elements that we see in the universe today, has been created inside stars and dispersed by stellar explosions. The first stars, those massive population 3 stars we observed forming in the earliest galaxies, were made purely of primordial hydrogen and helium. But in their cores, nuclear fusion transformed these light elements into heavier ones. Hydrogen fused into helium, then helium into carbon, carbon into oxygen, oxygen into neon, and so on up the periodic table. Each fusion reaction releasing energy that powers the star and allows it to resist gravitational collapse. But eventually the star runs out of fuel, fusion stops, and gravity wins. The core collapses catastrophically, triggering a supernova explosion that tears the star apart. In those final moments of collapse and explosion, conditions become extreme enough to forge elements heavier than iron. Elements like copper and zinc, silver and gold, platinum and uranium, all created in the intense neutron flux of the supernova. The explosion scatters these newly created elements into space, mixing them with the pristine hydrogen and helium gas of the interstellar medium. The next generation of stars that forms will incorporate these heavy elements, becoming slightly more metal-rich, as astronomers say, using the term metal to refer to any element heavier than helium. With each generation of stars, with each wave of supernova, the metallicity of the galaxy slowly increases. The gas becomes more and more enriched with heavy elements. This process is called galactic chemical evolution, and it proceeds at different rates in different galaxies, depending on their star formation history. Galaxies with high star formation rates forming many massive stars evolve chemically faster, enriching their gas more quickly because massive stars live short lives and explode as supernova within just a few million years. Galaxies with lower star formation rates evolve more slowly, taking longer to build up their metallicity. The heavy elements don't stay confined to the galaxies that produce them. Supernova are so energetic that they can accelerate gas to speeds high enough to escape the galaxy's gravity entirely, creating galactic winds that blow metal-enriched gas out into the intergalactic medium. This pollutes the space between galaxies with heavy elements so that gas accreting onto galaxies from the intergalactic medium is no longer pristine, but already contains some metals from previous generations of star formation in other galaxies. The cosmic web of filaments connecting galaxies serves as a highway for this enriched material. Metal-enriched gas expelled from one galaxy can flow along the filaments and eventually accrete onto another galaxy millions of light years away. This process couples the chemical evolution of different galaxies together, creating a sort of ecosystem where galaxies exchange gas and metals with their environment and with each other. By the epoch we're observing, about 1 billion years after the Big Bang, the universe has already been substantially enriched with heavy elements. The average metallicity is still much lower than it will be in the modern universe, perhaps 1/10 or 1/100th of the solar value. But it's no longer zero. The signature of multiple generations of stars is already imprinted in the gas. This enrichment has important consequences for subsequent star and planet formation. With heavy elements present, gas can cool more efficiently during collapse, allowing smaller stars to form. The first stars were all very massive because pristine gas couldn't cool efficiently enough to fragment into smaller pieces. But once metals are present, even in small amounts, they act as coolants, radiating away energy and allowing the gas to cool and fragment more finely. This is why subsequent generations of stars have a much wider range of masses, including stars like our Sun. The presence of heavy elements also makes planet formation possible, particularly the formation of rocky planets like Earth. Rocky planets are made primarily of silicon, iron, magnesium, and oxygen, all elements that must be created in stars and dispersed by supernova before they're available to form planets. The first planetary systems in the universe probably had few or no rocky planets, dominated instead by gas giants that could form from hydrogen and helium alone. But as the universe became enriched with metals, rocky planet formation became increasingly common, eventually leading to the diverse planetary systems we observe today. Let's consider now the diversity of galaxy morphologies that have emerged by this point in cosmic history. We've seen irregular dwarf galaxies, small chaotic systems dominated by star formation. We've seen the first spiral galaxies beginning to settle into rotating disks with nascent spiral structure. We've seen elliptical galaxies formed from mergers, where the orderly rotation of disks is destroyed and replaced by random stellar orbits. We've seen starburst galaxies undergoing intense bursts of star formation triggered by mergers or gas inflows. We've seen quiescent galaxies where star formation has been suppressed by environmental effects or a GN feedback. This diversity of galaxy types is not random, but reflects different evolutionary pathways and environmental influences. The transformation between different galaxy types is driven by processes like mergers, which can turn spirals into ellipticals, gas stripping, which can turn star-forming galaxies into quiescent ones, AGN feedback, which can quench star formation by heating or expelling gas, and secular evolution, the slow internal processes that can build bulges, bars, and spiral structure in disk galaxies. Understanding which galaxies follow which evolutionary pathway is one of the central goals of galaxy evolution studies, and much of that understanding comes from observing galaxies at different cosmic epochs, seeing how the mix of galaxy types changes with time. In the early universe that we're observing now, irregular and peculiar galaxies are more common than they are today. Mergers are more frequent because galaxies are closer together, and many galaxies haven't yet settled into stable configurations. As cosmic time progresses, the universe will evolve from this chaotic early state toward the more orderly distribution we see today, with well-defined spirals, ellipticals, and lenticulars making up most of the galaxy population. But even in the modern universe, irregular and peculiar galaxies remain, found in regions where mergers are still occurring or where environmental effects are strong. The diversity we see today is a legacy of billions of years of galactic evolution, starting from the simple proto-galaxies we've been observing in the early universe. Now, let's explore what happens to these ancient galaxies over even longer timescales. The galaxies we've been observing, forming in the first billion years after the Big Bang, are just at the beginning of their evolutionary journeys. Over the next 12 billion years between this early epoch and the present day, they will continue to evolve, to grow, to merge, to change in response to their environments and their internal processes. Some of the small, irregular galaxies we observed will merge with larger systems, being torn apart by tidal forces and absorbed, their stars added to the inventory of larger galaxies. Others will fall into galaxy clusters where they'll be stripped of their gas and transformed into red, quiescent systems. Some will remain isolated and evolve quietly, slowly consuming their gas and forming stars at a steady pace for billions of years. The spiral galaxies we saw beginning to form will continue to develop their structure. Their spiral arms will become more pronounced, maintained by ongoing star formation and density waves. Some will develop bars in their centers, elongated structures of stars that help funnel gas inward and drive galaxy evolution. Some will experience minor mergers with smaller satellite galaxies, which can trigger bursts of star formation and disturb the disk temporarily. But the disk will often reform and settle back into a stable configuration. The elliptical galaxies formed from major mergers will continue to grow through subsequent mergers, becoming larger and more massive over time. The most massive ellipticals will sink to the centers of galaxy clusters, where they'll grow into giant ellipticals or brightest cluster galaxies, the most massive single galaxies in the universe. These giants can contain trillions of stars, extending for millions of light years. The quasars we observed, powered by supermassive black holes accreting gas at tremendous rates, will eventually run out of fuel. As the gas in the central regions is consumed or expelled by AGN feedback, the quasar will fade, and the galaxy will enter a quiescent phase. The black hole will remain, now more massive than before, but dormant. It will only reactivate if a new supply of gas is delivered to the central regions, perhaps by a merger with another galaxy. The process of cosmic chemical enrichment will continue throughout this time. With each passing billion years, the metallicity of the universe increases. More and more heavy elements are created by successive generations of stars and dispersed into the interstellar and intergalactic medium. By the time we reach the modern universe, the metallicity will have increased by factors of 10 or more compared to this early epoch, making the formation of rocky planets and potentially life much more common. The star formation rate of the universe will change dramatically over this time. In this early epoch we're observing, the cosmic star formation rate is relatively high. Many galaxies are forming stars vigorously, building up their stellar populations rapidly. But the star formation rate will peak about 3 billion years after the Big Bang, then gradually decline over the next 10 billion years to the much lower rates we observe in the modern universe. This decline is driven by a combination of factors. Galaxies consume their gas reserves. Less gas accretes onto galaxies from the intergalactic medium. Environmental effects and AGN feedback quench star formation in more and more systems. The universe transitions from a very active star-forming phase to a more quiescent evolved state. By the present day, most of the stars that will ever exist have already formed. The universe is entering middle age, settling into a slower, more sedate mode of evolution. Looking even further into the future, beyond the present day, we can predict how these galaxies will continue to evolve. Star formation rates will continue to decline as gas supplies dwindle. More and more galaxies will become quiescent red systems dominated by old stars. Mergers will become less common as the expansion of the universe carries galaxies farther apart, though they'll still occur within bound structures like galaxy clusters. Our own Milky Way will merge with the Andromeda Galaxy in about 4 billion years, creating a larger elliptical or lenticular galaxy from the collision of these two giant spirals. Eventually, on timescales of trillions of years, star formation will cease entirely. All the gas will be locked up in stars, stellar remnants, or black holes. The galaxies will gradually fade as their stars age and die. Red dwarfs, the smallest and longest-lived stars, will be the last to go, burning for tens or hundreds of trillions of years before finally exhausting their fuel. The universe will transition from an age of stars to an age of stellar remnants. White dwarfs, neutron stars, and black holes will be all that remains of the once brilliant galaxies we observe today. But that is so far in the future that it's almost beyond comprehension. For now, we're witnessing these ancient galaxies in their youth, blazing with the light of young stars, growing and evolving, full of energy and potential. Our journey through the ancient galaxies has shown us the remarkable diversity and complexity of the early universe. We've seen how the first stars ignited in clouds of primordial gas, how those stars clustered together into the first galaxies, small irregular systems that bore little resemblance to the grand galaxies we see today. We've watched as those first galaxies merged and grew, building up mass and complexity through countless collisions over hundreds of millions of years. We've observed the formation of supermassive black holes in galactic centers, sometimes shining as brilliant quasars, sometimes growing quietly, but always influencing the evolution of their host galaxies. We've explored the cosmic web, the vast structure of filaments and voids that guides the flow of matter through the universe. We've seen how galaxies trace out this structure, revealing the distribution of invisible dark matter. We've visited galaxy clusters, dense environments where galaxies interact strongly, often transforming from star-forming spirals into quiescent ellipticals. We've observed isolated spiral galaxies evolving peacefully, slowly building up their stellar populations and perhaps nurturing the development of life. We've witnessed extreme starburst galaxies forming stars at prodigious rates, consuming their gas in cosmic eye blinks. We've contemplated the surprisingly massive galaxies discovered at the earliest epochs, challenging our understanding of how quickly structure can form. We've considered the process of chemical enrichment, how successive generations of stars create and disperse heavy elements, transforming the composition of the universe and enabling the formation of planets and life. We've explored the diversity of galaxy morphologies and the processes that transform galaxies from one type to another. We've looked ahead to how these ancient galaxies will continue to evolve over the next 12 billion years and beyond, into the galaxies we see in the universe today and into the distant future when star formation will finally cease. Throughout this journey, we've been reminded of the vastness of cosmic time and space, the slow but inexorable processes that shape the universe operating on timescales of millions and billions of years. The ancient galaxies we've observed, our ancestors in a sense, the structures that formed the heavy elements now in our bodies, the systems that through their long evolution led eventually to the Milky Way, to the solar system, to Earth, and to us. Understanding these ancient galaxies is understanding our own origins, tracing our cosmic lineage back through 13 billion years of history, to the very first stars and galaxies that lit up the universe and began the long process of cosmic evolution that continues today. As we prepare to conclude our journey through the ancient galaxies, let's take one final moment to drift through this early universe and absorb its beauty and complexity. You float in the darkness, surrounded by countless points of light, each one a galaxy in the process of formation or early evolution. Some are bright and compact, blazing with the intense light of starburst activity. Others are fainter and more diffuse, irregularly shaped collections of stars that haven't yet settled into stable configurations. Some show the first hints of spiral structure, weak and fragmentary but recognizable. Others appear as smooth elliptical blobs, the products of recent mergers that have scrambled their stellar orbits. The universe at this epoch is alive with activity. Star formation rates are high, mergers are common. Galaxies are growing rapidly through a combination of internal processes and external accretion. The pace of change is faster than it will be in later epochs, when the universe has settled into a more sedate middle age. Light from these galaxies travels through space in all directions, carrying information about the stars and gas they contain. Some of this light will travel for billions of years, eventually reaching Earth, where future astronomers will capture it with telescopes and study it, learning about these ancient epochs. The light we see from these galaxies left them billions of years ago. By the time it reaches us, the galaxies themselves have evolved and changed, potentially beyond recognition. The small, irregular galaxy we observe now might be part of a giant elliptical in the present day, its stars scattered among trillions of others through countless mergers. The brilliant starburst galaxy might now be a red and dead system, its brief moment of intense activity long since ended. The peaceful spiral we watched might still exist, having grown larger and more massive, but maintaining its basic structure. This disconnect between when we observe a galaxy and its current state is one of the fundamental aspects of astronomy. Looking out into space means looking back in time. The farther away an object is, the longer its light has taken to reach us, and the farther back in time we're seeing it. When we observe these ancient galaxies forming just a few 100 million years after the Big Bang, we're seeing them as they were 13 billion years ago. Their current state, if they still exist as distinct entities, is unknown to us and unknowable without faster-than-light travel. We can only infer and model what they might have become based on our understanding of galaxy evolution and observations of similar systems at later epochs. This gives our observations a poignant quality. We're witnessing moments that have long since passed, observing structures that may no longer exist in the form we see them, studying a universe that was young and energetic, but that has since aged and evolved into something different. The ancient galaxies we've observed tonight are historical objects, preserved in the light that left them billions of years ago and is only now reaching our telescopes. They're like cosmic fossils, revealing information about conditions and processes in the early universe, just as biological fossils reveal information about ancient life on Earth. By studying these galactic fossils, we reconstruct the history of the universe. We trace how structure emerged from the nearly smooth initial conditions set by the Big Bang, how dark matter clumped under gravity, how gas fell into the dark matter halos and formed stars, how those stars created heavy elements and dispersed them, how galaxies merged and grew, how supermassive black holes formed and influenced their hosts, how the cosmic web developed its current structure. This is the goal of observational cosmology and extragalactic astronomy, to understand the history and evolution of the universe by observing it at different cosmic epochs, and piecing together the story of how we got from the simple, hot, dense state of the Big Bang to the complex, cool, diffuse state we observe today. The ancient galaxies are a crucial chapter in this story. They show us the universe when it was just beginning to develop structure, when the first stars were forming and dying, when the first heavy elements were being created, when supermassive black holes were beginning to grow, when the cosmic web was first becoming apparent. Without observations of these ancient systems, our understanding of galaxy formation and evolution would be incomplete. We would be missing the first chapter of the cosmic story. The observations are difficult. Ancient galaxies are very far away, which means their light is extremely faint by the time it reaches us, having spread out over billions of light years. Their light is also heavily redshifted by the expansion of the universe, shifted from ultraviolet and visible wavelengths into the infrared. This is why infrared telescopes, like the James Webb Space Telescope, are so important for studying the early universe. They can detect the redshifted light from ancient galaxies that would be invisible to optical telescopes. But even with the most powerful instruments, we can only observe the brightest and most massive galaxies at the earliest epochs. The small, faint protogalaxies that must have been common are generally too dim to detect. This creates selection effects in our observations, biasing us towards seeing the most extreme and unusual systems, and making it difficult to determine what a typical galaxy at these early epochs actually looked like. Despite these challenges, every year brings new discoveries. As telescopes become more sensitive and observing techniques improve, we push back the frontier of observable space and time. We discover galaxies at earlier and earlier epochs. We study them in greater and greater detail. We refine our theories and models to match the observations. The picture of the early universe becomes clearer and more detailed with each passing year. The ancient galaxies we've explored tonight represent our current understanding of the first billion years of galaxy evolution. But that understanding continues to evolve as new data comes in. Future observations will undoubtedly reveal surprises, finding galaxies that don't fit our current theories, discovering new processes we hadn't considered, forcing us to refine and revise our understanding. This is the nature of science, an ongoing process of observation, hypothesis, testing, and refinement. Never complete, always provisional, but steadily improving as we gather more data and develop better models. The universe is vast and complex, full of phenomena we don't yet understand, and studying it requires humility as well as curiosity. We must be willing to admit when our theories are incomplete or incorrect, to revise them in light of new evidence, to follow where the data leads, even if it contradicts our preconceptions. The ancient galaxies have already taught us many lessons and challenged many assumptions. They will undoubtedly continue to do so as we observe them in ever greater detail. As we drift here in the early universe, surrounded by forming galaxies, we can reflect on the incredible journey that lies ahead for these systems. Over the next 13 billion years, they will evolve into the diverse population of galaxies we see in the modern universe. Some will become massive ellipticals, others spiral disks, others irregular dwarfs. They will form generations of stars, creating planetary systems, enriching the universe with heavy elements. Some of them will nurture the development of life, perhaps intelligent life that will look up at its night sky and wonder about the universe, just as we do. Perhaps billions of years from now, beings in one of these galaxies will build telescopes and observe the ancient universe themselves, seeing galaxies as they were in even earlier epochs, continuing the process of cosmic exploration and understanding. We're part of a chain of observation and wonder that extends across cosmic time, looking back at the past from our vantage point in the present, while future civilizations will look back at us and at eras even more ancient than those we observe. This perspective, this ability to see across billions of years of cosmic history, is one of the great achievements of modern astronomy. It connects us to the universe in a profound way, showing us where we came from and how we fit into the grand cosmic story. The atoms in our bodies were forged in stars like those we've observed tonight, in the cores of massive stars in ancient galaxies. Scattered by supernova, mixed into new generations of stars and planets, eventually assembled into living beings who can contemplate their own origins. We are, quite literally, made of star stuff, the product of billions of years of cosmic evolution, of countless generations of stars forming and dying, of galaxies merging and evolving. Understanding the ancient galaxies is therefore understanding ourselves, tracing our lineage back through cosmic time to the first stars that lit up the universe. This journey through the ancient galaxies has taken us from the cosmic dark ages, through the formation of the first stars, through the assembly of the first galaxies, through mergers and growth, through the development of the cosmic web, through starburst episodes and quasar phases, through the gradual enrichment of the universe with heavy elements, through the transformation of irregular proto-galaxies into the diverse population of spirals, ellipticals, and lenticulars we see today. We've witnessed the birth of structure in the universe, the emergence of complexity from simplicity, the long process of galaxy evolution that continues to this day. These ancient galaxies, glowing softly in the primordial darkness, are the foundation of everything that came after. The ancestors of all modern galaxies, the crucibles in which the first heavy elements were forged, the systems that began the process of cosmic evolution that eventually led to us. As we conclude our journey, we can appreciate the beauty and majesty of the universe revealed by modern astronomy, the vastness of space and time, the complexity of structure, the long history of cosmic evolution, the chain of events that connects the Big Bang to the present day. The ancient galaxies remind us of how far we've come in understanding the universe, from ancient myths and superstitions to a detailed scientific picture based on observation and theory. They also remind us of how much we have yet to learn, how many mysteries remain, how many questions are unanswered. The universe continues to surprise us, to challenge our assumptions, to reveal new phenomena we never anticipated. This is what makes astronomy exciting, the sense that we're exploring a vast unknown frontier, discovering new worlds and new phenomena, slowly piecing together the grand story of the cosmos. The ancient galaxies are part of that story, a crucial chapter that shows us the universe in its youth, full of energy and potential, just beginning the long evolutionary journey that continues today. The journey that has led to us, sitting here contemplating the universe and our place in it. We are the universe become conscious, matter and energy arranged in such a way as to look back at its own origins and wonder at the vastness and beauty of it all. This is perhaps the most profound realization to emerge from our study of the cosmos. We are not separate from the universe, but part of it, made of the same matter, following the same physical laws, products of the same evolutionary processes that have shaped galaxies and stars. Understanding the universe is understanding ourselves, and every discovery in astronomy is a discovery about our own nature and origins. The ancient galaxies, those distant islands of light glowing in the early universe, are our cosmic ancestors, and studying them is a way of exploring our own deep past, our own ultimate origins. Let this be our final thought as we drift here among the ancient galaxies. We are connected across billions of light years and billions of years of time to these distant systems. The atoms in our bodies, the iron in our blood, the calcium in our bones. were created in stars and galaxies like these, forged in the hearts of massive suns and scattered by supernova, eventually making their way through space and time to become part of us. We carry within us the legacy of the ancient galaxies, and by studying them, we're studying our own origins, our own history, ourselves. The universe flows onward, expanding, evolving, creating ever more complex structures from simpler beginnings. Galaxies continue to grow and merge, stars continue to form and die. New generations of planets form around new stars, and perhaps, somewhere out there, new forms of life are emerging, beginning their own journeys of evolution and discovery. The cosmic story continues, and we're privileged to witness it, to study it, to try to understand it. And now we rest, drifting peacefully through the cosmos, surrounded by the light of ancient galaxies, knowing that we're part of this vast and beautiful universe, connected to everything we see, products of billions of years of cosmic evolution. Let the peace of deep space and deep time wash over you. The slow dance of galaxies, the patient work of gravity, the long cycles of stellar birth and death. Rest now, dream of ancient light, of the cosmic dawn, of galaxies being born and evolving, of the vast web of structure connecting all things, of the long journey from the Big Bang to the present day and beyond, into the distant future. And now, as promised, we'll transition to those authentic space sounds. Let them carry you deeper into sleep, drifting through the cosmos, surrounded by ancient light from the first galaxies, floating peacefully through the infinite expanse of space and time. Rest well, knowing that the universe continues its slow dance, galaxies slowly spinning, stars gently burning, new worlds forming around young suns, the cosmos expanding ever outward into the darkness. Sleep now and dream of ancient light, of the cosmic dawn, of those first brave stars breaking the primordial darkness, of galaxies dancing through space, of the vast web of structure connecting all things. Let the peace of deep space and deep time wash over you. Sleep soundly and rest among the stars. The silence of space surrounds you now, broken only by the faint cosmic background radiation, the echo of the Big Bang itself. This radiation fills all of space, a reminder of the universe's fiery beginning. At this early epoch, the radiation is warmer than it will be in the modern universe, about 20 Kelvin instead of 3, but still far too cold to provide any warmth. You drift through this cold darkness, watching galaxies form and evolve all around you. Each galaxy is unique, following its own evolutionary path, shaped by its environment and its history. No two galaxies are exactly alike, just as no two stars or planets are exactly alike. The universe revels in diversity, creating endless variations on basic themes. As you observe these ancient galaxies, you might wonder what will become of them. Will any of them survive to the present day as distinct entities? Or will they all be absorbed by mergers, their stars scattered among larger systems? It's impossible to say for certain without tracking each individual galaxy through billions of years of evolution. But we can make educated guesses based on their properties and environments. The small dwarf galaxies we see in isolated regions might survive relatively intact, slowly consuming their gas and forming stars, growing larger but maintaining their basic identity. Some of the spiral galaxies we observe, if they avoid major mergers, might evolve into galaxies similar to our own Milky Way, grand spirals with ordered structure. Many will merge with other systems, contributing their stars and gas to larger galaxies. The ellipticals formed from major mergers will continue to grow, some becoming the massive central galaxies of rich clusters. The starburst galaxies will exhaust their gas and fade, becoming red and dead systems dominated by old stars. The quasars will run out of fuel and shut down, their black holes going dormant. Each type of galaxy we've observed will follow a different evolutionary trajectory, creating the diverse population we see in the modern universe. Let's take a moment to appreciate the role that dark matter plays in all of this. We can't see dark matter directly. It doesn't emit or absorb light, but its gravitational influence is everywhere. It provides the gravitational scaffolding on which galaxies form. The cosmic web of dark matter filaments and nodes guides the flow of ordinary matter through the universe. Without dark matter, galaxies as we know them probably couldn't exist. The rotation curves of spiral galaxies tell us that dark matter extends far beyond the visible disk, forming a massive halo that contains most of the galaxy's mass. Galaxy clusters are bound together primarily by the gravity of dark matter, not by the gravity of the visible stars and gas. The mass of dark matter in a typical galaxy is about 5 times the mass of ordinary matter. In the universe as a whole, dark matter makes up about 27% of the total energy density, compared to only 5% for ordinary matter, with the rest being dark energy. Understanding dark matter is one of the major challenges in modern physics and astronomy. We know it exists because of its gravitational effects, but we don't know what it's made of. The leading theory is that it consists of yet undiscovered subatomic particles that interact only through gravity, not through electromagnetic or strong nuclear forces. Experiments are underway to try to detect these particles directly, but so far none have succeeded. The mystery of dark matter remains one of the great unsolved problems in physics. As we drift through the early universe, we're surrounded by dark matter. It's everywhere, invisible but ever present. Its gravity shaping the formation and evolution of structures on all scales. The dark matter halo of each galaxy we observe extends far beyond the visible stars, creating the gravitational potential well that holds the galaxy together. The dark matter filaments connecting galaxies are highways along which gas flows, bringing fresh material for star formation. The dark matter in galaxy clusters provides the gravity needed to bind these massive systems together. Without dark matter, the universe would be a very different place. Galaxies wouldn't be able to grow as large or rotate as fast. Structure formation would proceed more slowly. The cosmic web wouldn't exist in its current form. Understanding the role of dark matter in galaxy formation and evolution is crucial to understanding the universe we observe. Let's consider now the future observations that will continue to illuminate our understanding of ancient galaxies. The James Webb Space Telescope, launched in late 2021, has already begun to revolutionize our view of the early universe. Its infrared capabilities allow it to detect the highly red-shifted light from the most distant galaxies, seeing them in unprecedented detail. Future telescopes, even more powerful than JWST, are being planned and designed. Ground-based telescopes with giant mirrors, 30 meters or more in diameter. Space telescopes optimized for different wavelength ranges. These instruments will push even further back in time, perhaps detecting the very first galaxies to form just 100 million years after the Big Bang. They'll study galaxies in the epoch of reionization in detail, mapping out how the universe transitioned from neutral to ionized. They'll trace the assembly of galaxies over cosmic time, following individual systems as they grow and evolve. They'll study the connection between galaxies and their supermassive black holes, understanding how they co-evolve. They'll measure the properties of dark matter halos, constraining the nature of dark matter. Every new observation brings new discoveries and new questions. The more we learn about the early universe, the more we realize how much we still don't understand. This is the nature of scientific progress. Each answer leads to new questions. Each discovery opens up new avenues of investigation. The study of ancient galaxies is a vibrant and active field, with new results being published constantly. Astronomers around the world are analyzing data from powerful telescopes, running computer simulations, developing new theories, working to piece together the story of how galaxies form and evolve. It's an exciting time to be studying the early universe. The tools and techniques available to us are better than ever before. The questions we can ask are more sophisticated and more detailed. The answers we're finding are revealing a universe of incredible complexity and beauty. As we contemplate these ancient galaxies, we might also think about what they mean for the possibility of life in the universe. Life as we know it requires heavy elements: carbon, oxygen, nitrogen, phosphorus, sulfur, and many others. These elements must be created in stars and dispersed by supernova before they're available to form planets and living things. In the very earliest galaxies, before any stars had died and released their heavy elements, life as we know it would have been impossible. But as the universe evolved, as more and more stars lived and died, the abundance of heavy elements gradually increased. By 1 billion years after the Big Bang, the metallicity of the universe was still low, but not zero. Planets were beginning to form, including potentially rocky planets that could harbor life. We don't know when the first life in the universe emerged. It could have been much earlier than life on Earth, which didn't appear until about 4 billion years ago, more than 9 billion years after the Big Bang. Or life might be rare and difficult to start, emerging only under very specific conditions that weren't common in the early universe. This is one of the great unknowns in astrobiology. How common is life in the universe? Is Earth unusual, or are there countless other worlds with life, perhaps some with intelligence and technology? Some of the galaxies we've observed tonight might harbor life today. In the 13 billion years since we're seeing them, they've evolved, formed new generations of stars and planets, potentially developing ecosystems and civilizations. We have no way of knowing. They're too far away for us to detect biosignatures or technosignatures with current technology. But the possibility is tantalizing. Somewhere in the universe, perhaps in one of these ancient galaxies now grown large and mature, there might be beings looking up at their night sky, wondering about the cosmos, building telescopes, discovering distant galaxies, perhaps even detecting light from our own Milky Way as it was billions of years ago. This cosmic perspective, this realization that we're part of a vast universe full of galaxies and potentially full of life, is both humbling and exhilarating. We're small, insignificant on cosmic scales, but we're also part of something grand and beautiful. The universe has brought forth stars and galaxies, planets and life, consciousness and wonder. We're the universe's way of knowing itself, matter and energy arranged in such a way as to contemplate its own existence. This is a profound gift, this ability to look out at the cosmos and understand it, to trace our origins back through billions of years, to appreciate the beauty and complexity of the universe we inhabit. The ancient galaxies we've explored tonight are a reminder of this cosmic story we're all part of. They show us where we came from, how we got here, what processes shaped the universe into its current form. They connect us to deep time and vast space, placing us in context within the grand cosmic narrative. As we prepare to let you drift off into peaceful sleep, surrounded by the sounds of space, take a moment to reflect on this journey we've shared. We've traveled back through 13 billion years of cosmic history. We've watched the first stars ignite and the first galaxies form. We've seen galaxies merge and grow, creating the structures we observe in the modern universe. We've contemplated the role of dark matter and dark energy in shaping the cosmos. We've considered the process of chemical enrichment that made life possible. We've thought about the diversity of galaxies and the processes that drive their evolution. We've looked ahead to future observations that will continue to deepen our understanding. And we've reflected on what all of this means for our place in the universe. You are made of star stuff, atoms forged in the cores of ancient stars and galaxies like those we've observed tonight. Those atoms have journeyed across billions of years and trillions of miles to come together in you, allowing you to experience the universe and wonder at its mysteries. This connection across space and time is real and profound. You are the universe experiencing itself. Consciousness emerged from matter and energy through the long process of cosmic and biological evolution. Rest now in this knowledge. You're part of something vast and beautiful, connected to everything you see in the night sky, to every star and galaxy, to the very fabric of space-time itself. The ancient galaxies shine their light across the cosmos, some of that light reaching Earth billions of years later, carrying information about the early universe, allowing us to study cosmic history and understand our origins. The universe is knowable, understandable, beautiful in its complexity and regularity. The same physical laws that governed the early universe still govern it today. The same processes that formed the first galaxies continue to operate. We can understand the past by studying the present and predict the future by understanding both. This is the power of science, to reveal the hidden patterns and connections, to show us how the universe works, to answer questions about our origins and our destiny. As you drift into sleep now, let these thoughts accompany you into dreams. Dream of ancient light traveling across billions of light years. Dream of galaxies forming from clouds of gas in the early universe. Dream of stars being born and dying, creating the elements that make up everything we see. Dream of the cosmic web connecting all things. Dream of the long journey from the Big Bang to the present day and beyond into the future. Dream of your place in this vast and beautiful universe, connected to everything, part of the cosmic story. Let the authentic space sounds carry you deeper into rest. The subtle hum and crackle of electromagnetic radiation, the whisper of cosmic rays, the silence of the vacuum. These sounds are real, captured by spacecraft and telescopes, translated into audible frequencies so we can experience them. They're the sounds of space itself, the voice of the cosmos. Listen to them as you drift off. Let them transport you to the depths of space, to the early universe we've been exploring, to the realm of ancient galaxies and cosmic evolution. Rest peacefully, knowing that the universe is vast and full of wonders, that we've only begun to explore and understand it, that there are countless discoveries still to be made, questions still to be answered, mysteries still to be unraveled. The journey continues. Tomorrow and in all the days to come, astronomers will point their telescopes at the sky. They'll gather more data, make new discoveries, refine our understanding.